Hi there, Turgeon here, bringing you physics from afar. This is about torque problems. Don't forget to rewind, pause, write those extra notes that aren't really extra notes. They come from really listening to the commentary. Here's a classic torque example that will help you solve what is a kind of mysterious problem for a lot of students. So imagine a situation where you have, and let me say, by the way, this is going to be very much related to the worksheet called Parallel Forces and Equilibrium, but this is a good setup. This seems mysterious because it seems like you have too much unknown information, but you have a 60 kilogram person standing at a board. The board can be, this beam can be assumed to be uniform, and this person is not standing in the middle of the beam. They're standing off center on the beam, and they're actually 1.3 meters from the left support, and the beam is 2 meters long. So one thing you want to be aware of right away is always think about the logic of the forces. So you might think about forces up and forces down. So we know we have two downward forces, which means 600 newtons and 200 newtons for the weight of the beam and the weight of the person. So we know we have these two downward forces, but we actually can't immediately find these because we don't know the exact percentage that each of those represents. So we know we need a total of 800 newtons, but we don't know what it is. So now I'm going to do this torque diagram. This is the part you really got to think about is, so we got the force weight of the beam, the force weight of the person, and we know that F1 we know that F1 and F2 are both going upward. We know that F2's probably got to be greater because this person's off center, so this person is closer to F2. Okay, now there is a center of mass principle going on here, and that is that if it's a uniform beam, the weight can be thought to act at the center. That's really important. Write that down, put stars around it. If it doesn't say anything about the beam, if it just says that this is a uniform beam, or it just says nothing, then you can assume all of the weight acts at the center. And as we've been talking about, in torque, that's really important, not only thinking about what forces are there, but thinking about where they act. That's super important. So I've already gone through the argument of how force up equals force down doesn't really work, but we want to think about the sum of the torques is equal to 0. It's one of the conditions of equilibrium. I prefer to write clockwise torque equals counterclockwise torque. That's sort of just a simpler problem solving approach, and I think a lot of students prefer that as well. Okay, let me tell you what I'm doing here. I'm now going to reveal that, but wait a second. If you look at this established pivot point, and this is one of the key aspects of this problem, I have to establish a pivot point. I'm picking this point where a force is acting because then I get to call that a zero torque. So I get to ignore that. So once I pick this as a pivot point, exactly where F1 is acting, I now have these two forces which would tend to make this thing rotate this way. Is it rotating? No, there's that paradox. It's not rotating, but if it did, it would rotate this way based on this pivot point. This would tend to make it rotate counterclockwise. So I have two clockwise torques, one counterclockwise torque. Okay, save yourself hours of frustration later and just pause the video and make sure you understand that. How did he know? How am I supposed to know that these two torques are clockwise and this torque is counterclockwise and this torque is 0? Pause the video, I beg you, and just make sure you understand why that's true. You can even flip it and say, well, what if we had made the pivot point over here on the other side? It won't let me grab that scribble dot. Okay. Okay, whoa, what's going on here? I'm just plugging in numbers. Okay, this is just plugging in numbers. This is just the force weight of the person. You could have just thrown in a 600 here if you wanted to right here. You could have just thrown in a 200 there if you wanted there. And why did I choose 1? Because it's 1 meter away from the pivot because it's acting halfway. This gives me a force number 2 of 480 newtons, which means now I can look up the up forces and the down forces. This is just logic. Like, you don't have to overthink this part. A lot of people just they're not sure that they're allowed to just use reasoning, and you are allowed to use reasoning here. The torque is not always as logical. 2 upward forces, 2 downward forces. My force weight 1 has to be 303.8. If you add these up, they add up to approximately 800. But I kept saying 800 because I was assuming using a G of 10. This is using a G of 9.8. So that's the 2 supports problem. Wait, what did I do? I just used torque clockwise equals torque counterclockwise, and I was really careful to go step by step, one piece at a time. Let me solve number 1 from this worksheet. And I'm going to solve 1, 2, and 7 from this worksheet. If you read number 1 carefully, it describes this situation. It didn't describe where the pivot point was, and I'm choosing to make it on the right just to show that I can make it wherever I want. And this should probably not have been red. The pivot point should probably have been like fuchsia or something. So that it describes a 300 Newton force, 400, 500. I've divvied up these locations, and let me peek to see what, I can't remember what the beam length was here. I can't remember what the beam length was. I think it was, okay, 4 newtons, and I just divided this up: 1 meter, 2 meter, 3 meters, 4 meters. And I'm writing out my conditions of equilibrium. This thing is in equilibrium. It's not accelerating rotationally, and it's not accelerating translationally. So it's not being like thrown up or down or left or right, and it's not rotating. So if I look at my torques equals 0, really what I want to do is think clockwise equals counterclockwise. So really these are the way that most people prefer to write that. And then I can just look. Okay, if that's my pivot point, I've got a clockwise torque and 2 counterclockwise torques. Okay, this force would tend to make it go clockwise. These 2 would tend to make it go counterclockwise, and the 500 is not even in the picture. So I can write that out. And I can see I have 1 clockwise torque and 2 counterclockwise torques. Then I can start writing this out, and I can say, oh yeah, I've got ooh, don't get lost in the rectangles. Let's not get, don't worry here. This is not that bad. We're just going piece by piece. So this is the single force, which is unknown, but when I think about it, it's got to be 1200 newtons. Okay, so just think about that. Pause the video, no big deal. It's got to be 1200 newtons because of these 3. So I don't know where it is though, R times F. This is clockwise. So here's this torque here, R times F. I don't know what R is. I don't know exactly where that's located from my pivot, but I know these 2 counterclockwise torques are 4 times 300 and 2.5 times 400. So I can see that this is 2.5 meters away from this. I can see that this 300 is 4 meters away from the pivot. Pause the video and just write down like, okay, he got those numbers because he just looked at the pivot. We're just going step by step. I took the 1200, I plugged it in because the upward force has to balance all these ones. Okay. Now I did a little bit of algebra, and I got 1.83 meters from the light end. Because if you think about it, yeah, I don't remember if I solved it the other way before or something, but let me think about that for a sec. Yeah, I was falling into one of those logic traps that I think a lot of students fall into. Just because this has a 500 Newton force, that's not the heavy end. There just happens to be another force there. The center of mass of this thing is 1.5 meters away from the end. So that means that this is the heavy end over here. So when I say light end and heavy end, in the way I have drawn this, this is 1.83 meters away from, yeah, I'm not feeling great. My brain is kind of foggy right now. if you look at where this F was, intuitively I made it closer to my pivot point. And it is 1.3 meters away from this pivot point, which happens to also be the light end. Now, here's the thing. This is a big source of confusion. Students get really, really confused about this, and they think they don't understand it because they're getting different answers. Like, I think it works out to be 2.17 if you put your pivot point over here on this side. Not a big deal. Students get really worried about this. It's not a problem. It's just make it obvious where your pivot point was in your drawing, and I'll be able to see that. I'll know there's two correct answers. It's just all about how you choose to describe where it's coming from. It's not a big deal. Okay, here's problem number 2. If I recall, this one's kind of similar. Yeah, it's saying where should we place this force and how much. Now, this is a uniform beam. So what I like to do sometimes is this is a 36 meter beam, and I like to just divide it up into fourths. 18 meters, 9, 27, right? And then this is like 12 or something, so it's a little past the 9. And I've chosen to make my pivot point here. Pivot point probably shouldn't have been red. It should have been like violet or something. Again, I'm going to go one piece at a time, just one at a time. I'm going to write down torque clockwise equals torque counterclockwise. The upward and downward forces, again, we're getting that thing where, oh yeah, the upward force has to be 1800 newtons to compensate for all these three. Again, rewind the video and just think about that for a second. Like, this upward force, they don't mention any other forces here. They're saying we've got these 3 downward forces and we need some other force to balance them out. It's got to be an upward force. So if you look carefully at my drawing, I've decided to make the pivot point on the left here. There's 3 torques that are described, and then there's a 4th that they're asking about. So these 3 torques all would make it rotate how? Think about it. Clockwise. So torque, 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 and then all balanced by one single counterclockwise torque. I like to just throw those in there and not worry about the subscripts. You can put subscripts if you need to. 12 times 600. Why did I do 12? Because they told me it was 12 meters. Why did I do 18? Because they said it's a uniform beam, so it's halfway, and that's the weight of the uniform beam. They told me this one was 27 meters away. I don't know how far away this force is, but I know it's got to be 1,800 newtons. Algebra. So I end up getting 20 meters from the left, which, if you think about it here, would be 16 meters from the right. Again, students really worry about this. They're like, oh no, what if I get this answer? I got 16, is that okay? Yes. I got 20, is that okay? Yes. But what do I do? What do I do? Just say what it is, left or right. I'm not trying to sound condescending. Like, I mean, I cared about grades. Like, I wouldn't want to get the problem wrong when I was your age, just because of some silly little like left-right thing or whatever, heavy end, or just don't worry about it. Like, just describe what you see. I clearly labeled my pivot point. You're good to go. This one's a little different. Well, I'd say it's different from the previous two. This is another 2 supports problem. So here's my non-uniform beam described in number 7, again from the parallel forces and static equilibrium. Here's my pivot point on the left. I don't know F1, so I like to throw my pivot point right there, right on top of a force that I don't know, so it'll cancel out. They tell me 1.1 meters away from one end is my 730 Newton weight. Remember that even though this weight's not evenly distributed, we can treat it as if it's acting at the center of mass. Here's the actual center of the beam. And here's the support, the upward support, the upward force from one of the people. I've drawn F1 larger than F2 because F1 is the heavy end. It's like you're carrying a couch or something. Like you're helping somebody move, and then like you're carrying the heavy end of the thing. Okay, so clockwise torques, counterclockwise. If I look at this problem, I see a clockwise torque and I see a counterclockwise torque. So it's pretty straightforward. There's only one clockwise and one counterclockwise. So my clockwise torque is 1.1 meters away. My video's ending in 4 seconds.